In this video, we're going to open the hood and take a look at the intricate code that powers an AI voice assistant. We'll run through everything from the very beginning, going from a clean repo to a polished wake word listener. We'll collect audio data, use audio processing to get features, build the neural network, train it, and build the listening engine to make predictions in real time. There are some great resources for different aspects of this project, but this video is going to bring them all together. When I was doing my research, there was some info about using machine learning on audio, but not nearly as much as computer vision or natural language processing. More than anything else, I struggled to find information on a real-time listening engine, especially an algorithm that would be performant enough to work on a Raspberry Pi. That's what's special about this video. I'll go over the details of creating the wake word listening engine, and we'll end up with concise and powerful code that's lightweight enough to easily run on a Raspberry Pi. Also, before I go any further, I need to mention how helpful the Mycroft open source project was. To learn how this works, I spent a lot of time going through the source code for their voice assistant. I've made another video about the theory and high-level logic behind the system, so if you haven't already, I would really recommend watching that first. We're going to dive straight into the code. First, we'll make a parameters file to hold all of the global parameters for file paths, how to sample audio, and how to convert audio into features for the model. The file parameters will include the directory that holds the audio samples for training, the training log directory, file names for positive, negative, and noise samples, and the path to where we're going to keep our optimized trained neural network. The audio parameters has info for how to sample the audio and convert it into features. We'll use the Pi Audio 16-bit integer format mono audio. Chunk size is the number of audio samples read from the microphone each time. Sample rate is how many audio samples to record each second. And features T is the time in seconds for a single input to the model. These next 5 parameters are specific to calculating the MFCC features. Window T is the size of the window for calculating the MFCCs in seconds. Hop T is the hop size, or how far to move the window when calculating the MFCCs in seconds. NMFCC is the number of coefficients to get from each window. For example, since we set this to 13, if we calculate the MFCC for one window worth of audio, we'll get an array of 13 numbers out. NFFT is how many samples to use in each Fourier calculation. And FILT is the number of filters to use in the MFCC calculation. I'm not going to go over what this means. It just has to do with the final steps of how the Mel scale spectrogram is converted into MFCC values. Then we'll make a constructor to take in all those values and define some properties. First is window samples. We already defined the window size in terms of seconds, so this will be the window size in terms of audio samples. Then hop samples is the same thing, but for the hop size. Then feature samples. Same thing, but for the features. This is the number of audio samples that will go into the neural network each time we make a prediction. And features is the number of different MFCC calculations that go into the model for each prediction. This is the number of windows of audio used for each prediction. To calculate this value, we use the window size and hop size in terms of audio samples to figure out how many windows will fit inside of feature samples. Together, NMFCC and NFeatures define the shape of the input to the model for each prediction. The numbers along the axis of size NMFCC make up the representation for one window of audio, and moving along the axis of size NFeatures is kind of like moving along time. Finally, we'll define chunks per sec, which is how many times we read from the audio stream each second. This is different from the sampling rate, because sampling rate defines the low-level rate of our computer reading a single sample from the microphone and storing it in an audio buffer. Our higher-level code will read multiple samples of audio at a time from the audio buffer, and chunks per sec is how frequently that happens. Now we'll just specify all those values. Chunk size is 1024 because the Raspberry Pi's audio buffer is 2048 bytes, and we're using an audio format of 16-bit or 2 bytes per sample. So if we read 1024 samples, that will empty the audio buffer on the Raspberry Pi. For the sampling rate, Google recommends using at least 16 kilohertz. The window size is 1/10 of a second, the hop size is 1/20th of a second, and we're going to put 1.5 seconds worth of features into the model for each prediction. We'll use 512 samples for each Fourier calculation, 20 filters for the MFCC calculation, and we'll get 13 coefficients from each MFCC calculation. So that's all the global parameters we'll need. Now we're going to write the code to collect training samples. First, we'll define some utilities, like saving a WAV file, creating a new audio stream to read audio from the microphone, and one last function to get the greatest index from the file names within a directory. Now we'll write some code to collect audio samples. First, we'll define some constants. The threshold is how loud the audio must be in order to trigger recording. Allowed silence seconds is how long there can be silence within one sample of recording. Min sample length is how short a sample can be. And finally, noise file length seconds is how long a noise file can be. Now we'll define an enumerator for the different ways that our noise collection script can run. Enter means save a sample every time I click enter on the keyboard. Threshold means save a sample every time the volume gets above the threshold. And noise means keep saving 15-second audio files till we quit. Okay, now we can go ahead and implement our sample collector class. The constructor will take audio parameters for how to record, file parameters for where to save the samples, one of those collection modes we just defined, and a boolean for if we're collecting positive or negative samples. Now we'll write the collection modes. First, we'll write the threshold collection mode. This is going to collect a sample whenever the volume exceeds the threshold. This is great because you can just talk without clicking anything, and you don't have to worry about getting the sound of your keyboard or mouse in the samples. Now we can write the code to collect the wake word when we press enter. I wrote this to record some samples of the wake word over background noise or stand in different places of my room saying the word. This time we're just going to save the exact amount of audio to input into the model, so 1.5 seconds. Last but not least, the function to collect noise. This is a lot simpler. We're just going to define how many frames of audio go into each file, then loop, recording audio, adding it to the frames, and saving a new audio file whenever it gets too long. Once we stop the process with the keyboard interrupt, we'll save the data. Now we can put it all together into the run function, which will create the stream, record the size of each audio sample, which is 16 bits or 2 bytes, then run the method corresponding to the run mode. We'll also want to define our init.py file to make it easier for the script to access the classes we just defined. Now it's easy to write the actual script that will run. It'll take the run mode and a flag for collecting negative samples. Then we just pass those to the sample collector and call run. Now I'll just actually use that script to collect samples. The first time I did this, I ended up collecting a total of 100 positive samples. First, I'll collect some using threshold mode, just saying the wake word with different inflections and different speeds. Then I'll use enter mode and try to make some background noise or even get up and walk around my room and take the recording from different places. If you don't have a wireless keyboard, this might be a bit more difficult for you. For the negative samples, I like to use this random word generator and set it to the same first and last letters and number of syllables as my wake word. Then go down the list recording the words. This is kind of like a stress test to get words that sound pretty similar but are different from the wake word. Then we want to collect some noise. This might not seem important, but when we're actually using our voice assistant, the vast majority of the audio it's picking up is just going to be ambient noise from your room. So it's really important that we train it not to activate on this noise. It's also an easy way to collect a ton of audio of your voice not saying the wake word. In addition to random noises, I recorded noise files of reading a couple pages of a book out loud. To wrap up the audio recording part, I'll write one last little script to make it easier to go through the positive samples and double check that they're all valid. It's possible to accidentally record a couple samples that were empty, and it's fine for those to be labeled negative, but we really want to try to avoid those being labeled positive samples. The script just iterates through the positive samples, plays them, then if you type anything other than just pressing enter, it will delete the file. Just to make sure that we have enough negative samples, and since this is so easy, I'm going to download the Common Voice dataset from Mozilla and save them in their own directory within the data directory. We don't really need that much extra data, and this is already going to vastly outnumber the samples I've recorded. So I'll just use the smaller dataset that's only about 1.5 gigabytes rather than one of the huge ones that's almost 80 gigabytes. Now that we have all the audio files for training, it's time to convert that into what we're plugging into the model. First, we're going to split the samples up into training, validation, and test sets. It's extremely important that the model is never trained on anything from validation or test, so we're going to make sure that those audio files stay completely separate. This data splitter class is going to split the data up into train, validation, and test sets, then save 3 separate CSV files, one for each of the data sets, containing the list of audio files in that set. The initializer will take the list of subdirectories that we created locally, meaning positive, negative, and noise, not including the downloaded data, then the list of percentages to use for the train, validation, and test dataset sizes. I'm going to use 80% of the data to train, then 10% each for validation and test. The split data function will perform all the high-level logic. We'll write these functions later, but at a high level, we're going to split each subdirectory into train, validation, and test, then figure out how many training samples each of those subdirectories is going to contribute to training. This is where we're going to get relatively small numbers for positive and negative samples, something in between for noise, and a much larger value for the downloaded data since there's so much of it. Then we're going to multiply the data that we have locally to compensate for how much more downloaded data there is. Then we'll save the respective CSV files. Create subdir datasets is what creates the list of file names for each dataset for each subdirectory. We'll loop over each of the subdirectories within the data directory, get all of the audio files, split them into train, validation, and test, then return the results. To actually split the files, we'll randomly shuffle them, figure out the number that go in each set, then divide them up and return the separate sets. Now we can get the number of training samples contributed by each subdirectory. We'll iterate through datasets from each subdirectory and look at the training set. If we're looking at the positive or negative sample directories, then we know each file will correspond to a single sample. If we're looking at a noise file or a downloaded file, then we'll need to open it up and check how long it is. To get the number of samples based on file duration, it takes a relatively long time to open up an audio file to check the duration. We'll assume that most of the files in the directory are the same length and just sample a quarter of them. For each of the files in the subset, we'll get the duration in seconds. From the duration, we can figure out how many MFCC windows can be calculated from that audio, then figure out how many inputs to the model correspond to that number of windows. Then it comes to multiplying the training sets. We're going to multiply the number of files in the training sets created locally so that each created locally is the same size as the downloaded data. For example, if we have 10 positive files, 20 negative, 25 noise, and 100 samples of downloaded data, we'll multiply the positive, negative, and noise by their respective values so that we have 100 samples of each. For each subdirectory, we'll calculate the multiplier based on the number of samples, then multiply the training data. Finally, we'll save the separate datasets into CSV files. The columns of the CSV files will correspond to the audio file names, the label corresponding to the file, so either 1 for positive or 0 for negative, and a flag for data augmentation. We only want to perform data augmentation on the samples that we created locally, since there's already multiple of each in the training set. Then we'll stick all the positive and negative samples together, shuffle them, then save them into a CSV file. Now we can write the script. We'll define the percentages for each of the datasets, 80, 10, and 10, like I said before, define the directories we created locally, and call the split data function. When we run the script, we'll now have 3 different CSV files, one for each of the datasets. Now that we've figured out how to divide the audio files into datasets, we can convert the raw audio into training features. Ultimately, we'll end up with one huge NumPy matrix for each dataset, saved in a .npy file. We'll start by writing the data augmentation functions. For noise injection, we'll generate a random noise signal, then add it to the audio data. For change speed and pitch, we'll just use functions from the Labrosa effects library. Then I'll write a script to demo the waveform augmentation by opening one of our positive samples and playing what it sounds like with each of the augmentations. For the spec augment function, I pretty much just copy and pasted this from Kaggle, and I've included the link at the top of the file. Now we'll make an audio conversion file that will have all of the code to convert from a NumPy array of audio samples into the input features. To convert the audio to features, first we want to randomly choose an augmentation type. Then, if the augmentation type is one of the waveform augmentations, we'll perform the corresponding one. For the positive or negative samples, where each file should correspond to a single input, we'll cut off the beginning of the file so that it's exactly feature samples length. Now we can calculate the MFCC values from the audio waveform. This function is just going to call the SonoPy library with values from the audio parameters we defined. After we have the MFCC values, we'll perform the spec augment, if that's the augmentation type, then reshape the MFCC to fit into the model. To reshape, first we'll pad the beginning with 0 values to make sure it's long enough. We'll make sure the MFCC length is evenly divisible by inputs to the model. Now that our matrix is the correct length, we'll reshape it so that the first axis is the individual inputs, the second axis is the time windows within the input, and the last axis is the coefficients for a single window of time. Now we're done, and we can just return the formatted features to input into the model. DataLoader is going to use everything we just built to take in the CSV files with the datasets and save a .npy file with the features for each set. This process can take a while, so I'm going to use 2 different threads, so the process continues while we're waiting to open audio files from disk. The DataLoader is just going to do one dataset at a time, so it'll take in the path to the CSV file for the dataset. We'll make a long list for the threads to share of all the files in the training set with their label and augment flags. Load data starts the threads, waits for them to finish, then concatenates all the data together and returns the matrices. What's going to happen inside the threads is pop a file path, label, and augment boolean off the files to load list, load the audio from the file, and convert the audio into features using the function we just wrote. So that's the input matrix. Now we have to define the output matrix. This is going to be the value 1 for each of the inputs if this is a positive sample, or 0 if it's a negative sample. Then we just add the input and output matrices to our combined list. We'll quickly write some functions to load audio from a file and print the progress throughout the process. We'll write the init.py file so that our script can access everything. In the script for preprocessing the dataset, we're going to take an argument for which dataset to use, either train, validation, or test, then call the data loader to get the input and output matrices. In machine learning, these are usually just called X for input and Y for expected output labels. Then we'll save the matrices to .npy files. Alright, we've gotten to the machine learning part. TensorFlow makes this easy for us, and it'll take much less code compared to what we've already done. Since it's so much less code, I'm going to do this part in a Python notebook to make it easier to see what happens at each step. First, we'll do the easy part and load the data that we just created from the .npy files. Then we can create the structure for the CNN we'll be using. I just copied this from the TensorFlow Recognizing Keywords tutorial. I had to change the input shape, the number of time windows, by the number of coefficients. Instead of using categorical cross-entropy like in the tutorial, we're only using binary cross-entropy, since there's only two options, wake word or not wake word. Then we'll do some more setup for training. The batch size will be how many samples we simultaneously train on. If you're lucky enough to have a GPU, that can speed up training a lot. I made this number as large as I could while still fitting in my GPU's memory. You'll want to tune this based on your computer. Epochs is how many times we'll run through the whole training set. If we had a smaller data set, we might want to set this to a bigger value. But since we already did a lot of multiplication of our data, this can be a pretty low value for us. Then we'll just set a name for the save directory of the model. Then the checkpoint callback will save the model itself. We'll only save the best model over all the epochs of training based on the validation accuracy. Finally, we'll actually train the model. This will take a bit of time. Since we've passed in validation data to the training function, at the end of each epoch, it'll print the validation loss and accuracy. If we're doing everything right, we should see the validation loss go down with each epoch. And it's done training. Now we have a trained neural network for detecting a wake word. Just for a sanity check, we can evaluate it on the validation loss again and make sure that it's the same as the last epoch. We can also test making predictions with the model now. I'll plug in the first 10 training samples, then print the corresponding labels. Looks like it got everything correct, although this isn't surprising since this is the training set it was optimized for. As a little experiment, I'm going to try making a slightly smaller version of the model. I'll keep everything the same, except for the convolutional layers, I'll use half as many filters, so 16 and 32 as opposed to 32 and 64. We'll set up the same checkpoint for training, we'll train for the same number of epochs and with the same batch size. Looks like this is also able to get good accuracy, but I'm going to stick with the slightly bigger model for now. Once it's optimized, even the larger neural network takes up less space in memory than just the Python files we've written so far. Well, that's it. Now we have a trained neural network. All that's left is to make the listening engine that can run in real time to detect the wake word. The first step towards using our model is going to be optimizing it with TensorFlow Lite. To do this, I'll just write a little function that loads the model, uses the TensorFlow Lite converter on our model, then saves the new optimized version. Now I'm going to define a model wrapper object. This will make it easier to use the model to make predictions later, and will handle the differences between loading and running the model depending if the listening engine is running on a PC or the Raspberry Pi. We'll define two different subclasses, one for running an unoptimized Keras model and one for a TensorFlow Lite model. The Keras model is easy. Just load the model from the file, then whenever we want to predict, we call predict on the model. The TensorFlow Lite version is a bit more complicated. First, we'll need to load packages differently depending on if we're running on a PC or the Raspberry Pi. We'll have to use different versions for the TensorFlow package. Then we'll have to do some initial setup to allocate the input and output tensors before we can make a prediction. When we make a prediction, we'll set the input tensor to the input features from the audio data, invoke the interpreter, then get the output tensor and return the prediction. Lastly, we'll make a handy function that can just take an arbitrary path and will return the right type of model wrapper based on the path. What we've all been waiting for, creating the listener engine. First, we'll make an activation trigger that will figure out if the voice assistant should wake based on the prediction of the neural network. The sensitivity will be how close the prediction needs to be to 1 in order to be considered an activation. A sensitivity of 0.3 means the prediction has to be greater than 0.7. The trigger level is how many activating predictions need to be seen in a short window of time in order to wake. Activation delay is how long after an activation we should wait before activating again. We'll keep track of an activation counter, which is how many times there's recently been an activation. This object basically keeps track of the previous predictions, so the check trigger function only needs to take in the most recent recent prediction. This chunk of audio is an activation if the probability is within the sensitivity value. If the chunk is active or the activation counter is negative, we'll increment the activation counter and check if the counter is greater than the trigger level, so 3. If there was an activation and we're still within the delay period, we'll reset the counter to a negative value. If it activated, we'll return true, indicating the voice assistant should wake up. If this chunk of audio didn't create an individual activation and the activation counter value is positive, reduce it by 1. Personally, when I was creating this, I felt like there was a lot of resources for how to do everything up to what I'm about to talk about. And I thought it was way more difficult to figure out how to do this next part. It wasn't quite as intuitive for me. We're going to create a wake listener object to handle the logic of the listening engine and keep track of the state. The audio buffer will hold the audio samples recorded from the microphone. This is initialized to an empty state since we haven't recorded anything yet. The input features variable is the feature matrix that's put into the neural network to get out a prediction. This is initialized to zeros, almost as if there was silence leading up to starting the engine. Feature audio and last activation audio are just used to save the most recent audio capture that resulted in an activation. I haven't done anything with this yet, but I want to set up a system to save false activations to use in further training of the model. The wake listener object itself won't directly be reading from the microphone. A loop that we will write later is going to read from the microphone, then pass the audio data to the check wake function. This function will return true if it should wake and false otherwise. I'll implement this higher level function before digging into how we're going to get the features. We're first going to get the MFCC features from the audio data, use the features to get a prediction from the model, check if the prediction results in a wake trigger, then return if there's a trigger. That's all. Now that leaves the last hard part that we haven't really talked about yet, getting the features. We'll convert the audio bytes into a NumPy array, then stick that onto the end of our audio buffer. Remember, in the parameters that we defined at the very beginning, the window samples value is how many audio samples go into a single window for the MFCC calculation. It's not possible to calculate the MFCC values without at least that much audio. So if we have enough audio, we'll get the MFCC values. This is done exactly the way we did it before, using the right audio parameters to call the SonoPy library. Once we have the MFCC values for what's currently in the audio buffer, we'll figure out how many audio samples we can throw away. Each time we calculate MFCC values for a window of audio, we move the window by the hop size, which is much smaller than the window size. In our case, the window size is 1/10 of a second, and the hop size is half that, 1/20th of a second. For each of the new features we calculated, we can get rid of 1 hop worth of audio. We'll actually save that audio for reference later, but we can remove it from the audio buffer. On the off chance that the new features are too long to fit into a single input to the model, we'll trim off the oldest parts. Then we just add the new features into the end of the input feature matrix, throwing away the oldest features so that it stays the same size. And then we return the input feature matrix. That's it. The absolute last thing we have to do is write the run listener script. This will be much more straightforward than the wake listener object. We're just going to load our trained model, create the audio stream from the microphone, then create our wake listener object with the model. We're going to create a thread so that the main thread can listen for user input to know when to quit. The thread is just going to read audio data from the stream, then pass it to the wake listener and check if there was a wake. If there's a wake, we'll run whatever code we want. That's it. Then we just have to start the thread, wait for the user to press enter once they're done, and clean up. And that's a wrap. We've gone through the maze of AI wake word detection, and I hope you got a clear picture of how the feature matrix, neural network, and listening engine all come together to bring this project to life. I was inspired to create this video because I couldn't find clear resources on maintaining the feature matrix and achieving real-time predictions, so I especially hope this video sheds some light on those aspects. I know I still haven't showed how I implemented the command handling, and I'll show that soon in another video. Thanks for watching.